also work out an example problem, just like I did last lecture in some detail, because it's directly applied to the homework that will be due next Tuesday, the last lecture. And then the other second half, I'm going to go back and make sure I answer any question you have for the homework due today, which is the inclined plate, and make sure that everything is clear. And then I will use that to look at the new homework due next Tuesday, which is problem 79 and 56. If time permits, which I doubt, I will go over the handout that I posted on Canvas. If not, we'll do it at the last lecture. So last lecture essentially is first and foremost go through a review of the whole semester. It won't take very long, maybe about 15 minutes. And then the remaining time I may do evaluate handout or other topic that you will still be responsible for the final exam, but in essence, no substantial new materials. Any question on the move forward plan regarding how the semester is wrapping up? Homework, last assignment is 3 problems, 2 hours, due next Tuesday. I will touch on each one of them in the lecture, so it will not be too taxing for you. And the reading is the posted handout on boundary layer analysis. So I have asked Mike to post on Scholar, or Canvas rather, that I added additional office hour between now and the final exam. The important one that you want to bear in mind is I schedule a study session just like we did for test 1, the night before final exam. And the location will be announced once I get the room. And for those who need some time for answering questions, feel free to attend. In the middle of this lecture, when I wrap up the hydrostatic, I want to present some overhead in reference to the Hoover Dam, which is, I hope, related to the hydrostatic that we'll be studying. And also some problem that we use computational fluid dynamics in real engineering application to get motivated as to why we spend so much time on all these Navier-Stokes equations. Okay? Any question before I start? Any administrative questions? Yes?
Do we know the location of the final?
Location of file is right here, just like any other classes. And it's on, and you should have that on Canvas, it's on Friday, the night after the help session. Friday morning, 7:45. 2 hours, right here. Okay? Any other questions? All right, so first, before I touch on the homework due today, any question on any aspect of what I've done on hydrostatic based on last lecture? There are a lot of new material for you, but I'm trying to pare it down to it directly relate to your static, The only change is all the forces now is due to water. Yes?
Did you say the review session is here too?
No. The final exam is here.
And the review session?
The review session is to be determined,
Right.
because I haven't got a room yet. And that will be all announced and post on Canvas. So are all the additional office hours. I don't want to wait out, you just check Canvas. Every day between now and the final exam, there's 1 office hour, in addition to what Mike has. So you should allow plenty of time for you to come ask questions on the lecture or preparation for final, or more importantly, use me for career advices, right? So any question on what we covered last time on hydrostatic? Do you understand the concept of what I call a pressure prism? Any question? Can you comfortably calculate the average pressure based on that, and then the force, which is pressure times an area, and then the moment arm, which require you to know the center of pressure or the location of the resultant force. All these are just static. Any question? No, very good, okay. So the next problem is a little interesting, but prior to that, I just want to reinforce what we did last time in reference to the homework due today. And an inclined plate is different from a vertical upright plate in that the pressure prism is simply rotated, and all the forces you still have to add. Normal and perpendicular. No change in the depth h. Okay? That you will need for your next homework. And the only change is the area. wetted area, when the plate is inclined, is bigger. Do you see that? Any question? You have done the homework, I'm just reinforcing the most important critical element. Yes?
So one question I had with this homework, when you're doing the force analysis,
Uh-huh.
or like a static analysis, do you have to account for the weight of the water on the incline?
Ooh, no. So this is a very important question. First, this is different from my homework, for my in-class problem, in that there's the weight of the gauge, okay? The weight of the water is all being translated into a pressure, okay?
Okay.
So you don't want to double count. There's no such thing as the weight of the water per se. It's all being reflected in the pressure acting on the gauge. That's what this is. So don't confuse yourself by looking at the weight of the water. It's totally irrelevant. All right? Other questions? So what we'll do now is to build on this and make some more interesting engineering application of hydrostatic. I should point out to you the solution which will be posted today at the end of the lecture. The solution is actually very different. They use all the formulae given in the textbook. Don't use them, forget it, don't worry about them, because we don't have time to derive those formulas. I feel this basic approach is even more relevant. So just check the answer. If you cannot get the right numerical answer and you are confused of how to do the problem, see my or see me. All right? So I hope that clarification is important for you to bear. In the final exam, obviously, that's the approach I want you to take. Just some basic static looking at the problem. Oh, I should mention too, class evaluation is end on December the 6th. Right now, it's about 15% of you have done it. Please do it. I take those seriously. I look at them and I take your input to improve the teaching. So I hope you are able to do that at home and be able to finish it before December 6th. All right? I think if you're familiar with that, I don't have to go over any of this aspect. So please do me a favor by filling those in. So a new problem, which will be directly related to your homework, is laid out like this. I have water on the west side of 2.1 liter. And I have a gauge that's hinged not at the bottom, but about 8-10 liter from the bottom. So the plate now is not completely from top to bottom on the wetter side, but instead I have now a gauge that is hinged kind of somewhere in the middle of the water. And in this diagram, I'd like to know what is the force that I need to apply at the base of this gauge for equilibrium. Let me give you a chance to understand the physics of the problem. So without that force F pointing to the left, the gauge will spring open. Why will it spring open? Well, because the hydrostatic pressure on the west side of the gauge will push it to the right. All right? So how is that different from the previous problem? Now I have a partial submerged gauge. And above that, I have also water. So we kind of take a little different spice to what we have used to see. Okay? So let me walk you through this homework, or rather this example in class. I'm going to draw the pressure prism, pretending that I'm going from top to bottom, an overall height or depth of 2.1 meters. Do you agree with that? from that, the difference in this problem is the hydrostatic forces that I'm concerned with only act on the 0.8 meter part of the water. Those above have no bearing on my problem. So that new twist forced me to look at the problem slightly differently than what I've done before. And what I would like to propose is that I use superposition, or loosely called divide and conquer, one piece at a time. I'm going to ask myself, for this 1/8 of a meter depth, that is of interest to me for getting the force F, what will be that pressure distribution look like? Trapezoid, very good. Basically, take that part and translate that over to here. Pretty straightforward. Do you agree? Anyone have a problem visualizing this? From here on, my only twist to the problem is I'm going to take this trapezoid and use divide and conquer, or superposition. I'm dividing them up into two pieces. One is a right angle triangle, and we deal with that last lecture and in your homework. I'll call that piece here 1. So I'm proposing I will use that triangle, right angle triangle, to find one piece of the force. I call it F1, solely due to this upright triangle. And then when I'm done, I'm going to look at my second piece. I'll call it F2, which is from a rectangle. And the hinge here is 1, 0. So let me make sure you understand the roadmap. Once you do, the rest is very simple. Once you see how we can visualize the problem as having two pieces add together, just like a puzzle that you put the pieces together one at a time, then the move forward roadmap is basically repeating what we've done before. Do you see that? Any questions? Yes?
So in this case, for the pressure from the water, you can no longer use 1/2, right? You have to solve for the average and just that 0.8.
Yeah, the question is now the next step. How do we proceed to solve the problem? So that is what we're going to do next. We're going to do the rectangle first, and then we're going to deal with the triangle. And to answer your question, deal with the triangle, I will basically use the same approach we did last time, in the last lecture. And then when I come to that part, your question will be answered. What is the average pressure now for this new triangle? Takes a little bit more twist, but it's fundamentally the same. Yes?
Yeah, what's the difference between the 2 meter depth and like the 2.1 meter triangle?
Oh, okay, so the height of the overall water from top to bottom is 2.1 meters. Obviously, I didn't draw this to scale. This is too big. The 2 meter depth, what does that mean? Into the paper. Right? And which will be needed when we get to calculate the force, because I need an area. An area consists of a length, which is the height, and the depth. So that will come into play momentarily. Okay, so any other questions? Now, let's deal with the rectangle. For that, I'm going to ask you, can you, based on the diagram, and tell me what is the magnitude of the pressure of this rectangle, which is same pressure everywhere? In other words, what is the rho GH? Pressure is rho GH, right? Rho GH. What's that H?
Big height minus small height.
It's the difference between the overall depth, top to bottom, 2.1, minus the height of that gate, which is 0.8, and that happened to be 1.3 meter. See that? Anyone? So then, when I look at the forces in total, F1 and F2, I'm now dealing with the F2 force. I have a pressure, 1.3 meter, where does that come from? Right here. Right, and forget the triangle, just look at this and ask yourself, can I calculate the resultant force due to this uniform distributed pressure, which is given by rho g times 1.3 meter times an area. What's that area? The height of the gauge times the depth into the paper. So that will be 0.8 times 2 meter squared. Questions? Questions? Okay, now come the more challenging part, right? Which is the triangle, which is the pressure prism. Yes?
I'm just so confused why the height isn't just 0.8, like why it's 1.3.
Okay, so the question is, why isn't the height 0.8 meter? The reason is the gauge here doesn't stop at atmospheric pressure. Above that, I have another column of water of depth from the top to the bottom. In other words, what is the I'm trying to redraw a totally different diagram to help you to understand. Hopefully I'm successful in doing that. Kind of looking at the problem a little differently. I have 0.8 meter on the uniform. I have 0.8 meter depth on this water tank. What is the pressure right at this 0.8 meter from the bottom? I will need rho g times whatever height I have from the free surface, which is 1.3 minus 0.8. Does that help? Does that help? Right? And that pressure, once I determine what it is, for this rectangle, that pressure is the same. Yes?
How come it would be the same if you took rho g h to the bottom point? Wouldn't it be more than 1.3? It would be rho g times 3.
It's the same because I cheated. When I say it's the same, I'm taking this pressure distribution, which is the shape of a trapezoidal. I'm breaking up into two pieces. The two pieces are, number one, a triangle, right-angle triangle pressure prism. Number two, a uniform pressure that I'm pretending to pick this and break it up. I'm breaking it up and use superposition to deal with one piece at a time. Use this first, which is what I'm doing right now. I'm going to ask myself, for this uniform pressure, what is the resultant force? It will be an area times a pressure of rho GH of this uniform distribution.
But wouldn't rho g h change as you go?
It changed, but that's the second piece that we'll deal with later, which is now this triangle. Do you see that? I'm breaking it up. The actual pressure distribution is dictated by this shape. Do you you see that? That is the resultant pressure distribution that I have to deal with because now the hinge is below the free surface of the water. But this outward shape is something that I'm not familiar with and comfortable with. So by taking advantage of superposition or divide and conquer, I want to deal with this in 2 steps. One is ask myself what is the resultant force due to this rectangle. That's what I just showed you. And then when I'm done with that, I'm going to ask myself how is the second piece will constitute to the resultant force. And that's the next step. Do you see that? It's not transparent, and that's why I'm taking a little time to slow down to make sure you can relate. Anyone have questions? Yeah.
I'm just wondering why the result, we're taking the height at the top of the rectangle rather than the centroid of the rectangle.
This one?
Yeah, why is the height H 1.3 instead of 1.7, which would be the middle?
1.7. This 1.3 comes about from the overall depth of the water minus the height of the gauge because I'm interested in the pressure right at this point. Right at this point. So this diagram I hope help to relate. Right? So forget that diagram, just ask if I am at this location, what is the pressure and it's given by rho GH, which is 1.3 minus 0.8. Right? So I have a pressure here at the starting point on 0.8. As I go further down, it will continue to increase by the relation of rho GH again. And that's this diagram. Right? So the bottom line is I'm simply breaking up into 2 pieces in order to work the problem. It's a little daunting. Yeah, I can see why you're confused. But any other question before I go on? Because to get piece 1,